can derive the relation between torque and angular momentum. We know torque is the rotational analog of force, isn't it? And angular momentum is the rotational analog of momentum. We know torque is given by the formula torque toe equal to R cross F. Vector toe equal to R cross F. And again we know angular momentum. Angular momentum, we know it is the rotation analog of momentum, and it is also called moment of momentum. And angular momentum is given by L is equal to R cross P. Clear? Now we can derive the relation between torque and angular momentum. We differentiate L equal to R cross P. We know angular momentum L equal to R cross P. Now we can differentiate L equal to R cross P with respect to time. So we can differentiate like this: d by dt of L equals d by dt of R cross P. Okay. So d by dt of R cross P, it can be differentiated like this: dr by dt cross P plus R cross dp divided by dt. This is the method. D by dt of R cross P can be differentiated like this: dr by dt cross P, that is the first term, plus R cross dp by dt. This is R cross dp by dt, cross product. So dl by dt, that is differentiating angular momentum with respect to time. dl by dt is d by dt of R cross P, and this can be differentiated like this: dr by dt cross P plus R cross dp by dt. But we know velocity v equal to this dr by dt. Velocity is dr by dt, isn't it? So this term can be written as dr by dt cross P is equal to, what is this dr by dt? Velocity, v cross P, or it can be written as v cross, momentum is mass into velocity, isn't it? So here velocity cross mass into velocity. Here velocity, the direction of velocity, here the direction of velocity and momentum are in the same direction, isn't it? Velocity and momentum are in the same direction. So what is the angle between them? Theta is 0. So we know that v cross P can be written as, what is this v cross P? Vp sin theta. Here velocity and momentum are along the same direction, isn't it? And hence theta is equal to 0. Therefore what is this value? dr by dt cross P is 0, because velocity and momentum are parallel to each other. Therefore theta is, what is the value of theta? Theta is equal to 0. Both are parallel, no? So velocity and the momentum are parallel to each other. Therefore theta is equal to 0, and hence dr by dt cross P is equal to 0. Therefore this term vanishes, and hence therefore we can write dl by dt is equal to d by dt of R cross P is actually R cross dp by dt. This term becomes 0. So it is equal to R cross dp by dt. And we know R dp by dt, rate of change of momentum. What is this rate of change of momentum? Rate of change of momentum is actually the force, isn't it? Hence we can write the relation dl divided by dt is equal to R cross dp by dt, but dp by dt is equal to force. Therefore it can be written as R cross F. And what is this R cross F? We know R cross F is equal to torque. Clear? Now we can write the relation dl divided by dt is equal to R cross F, which is torque toe. So the relation between torque and angular momentum is toe equal to dl divided by dt. The rate of change of angular momentum is actually the torque. And from the rotational motion, in the rotational motion we know torque is equal to rate of change of angular momentum. In linear motion, what is force? We know force is equal to rate of change of momentum. In linear motion, straight line motion, force is rate of change of momentum. In rotational motion, torque is rate of change of angular momentum. Thus, the rate of change of angular momentum of a particle is equal to torque acting on it. This is rotation analog of F equal to dp by dt. So, in linear motion F equal to dp by dt, and in rotational motion tau equal to d L divided by dt. In rotational motion, torque tau equal to dl by dt. So this is the relation between what torque and the angular momentum. Now we can discuss what is the law of conservation of angular momentum. In the chapter laws of motion, we have seen what is the law of conservation of linear momentum. That means when net force is equal to 0, here net force is equal to 0, momentum remains a constant, isn't it? Total force is equal to 0, the momentum of a system remains a constant. So here law of conservation of angular momentum states that if torque equal to 0, external torque equal to 0, angular momentum remains a constant. We have the relation between torque and angular momentum tau equal to dl by dt. Rate of change of angular momentum dl by dt is equal to the external torque. If the external torque is equal to 0, what happens to dl by dt? dl by dt is equal to 0. dl by dt 0 means L remains a constant. So the differentiating any constant is equal to 0, isn't it? Differentiating a constant is equal to 0, that means L remains a constant. So this is called law of conservation of angular momentum. If torque equal to 0, angular momentum remains a constant. Thus if the external torque on a system of particles is 0, then the total angular momentum of the system is conserved or remains constant, and this law is called law of conservation of angular momentum. If external torque equal to 0, angular momentum of a system of particles remain constant or conserved. We have tau equal to r cross f. From the figure it shows that tau is perpendicular to the plane containing r and f. Similarly, if you see angular momentum and momentum, angular momentum is perpendicular to the plane containing r and p. Now we can discuss what is equilibrium of a rigid body. We know what is a rigid body. It's a body having definite and unchanging shape, that is called a rigid body. When an external force is applied to a rigid body, it can execute two types of motion. First one, translatory motion, second one, rotatory motion about its own axis. So these are the two motion common for a rigid body. A rigid body is said to be in mechanical equilibrium if both its linear momentum and angular momentum are not changing with respect to time. So if both angular momentum and linear momentum of a rigid body remains constant with the time, then we can say that the rigid body is said to be in mechanical equilibrium. Okay, so a rigid body is in mechanical equilibrium if both linear momentum and angular momentum remains constant or they are not changing with time. Mechanical equilibrium means if linear momentum remains constant, that is one type of equilibrium. If angular momentum remains constant, that is another type of equilibrium. Okay, so if linear momentum of the body remains constant, how the linear momentum can be kept constant? If total force is equal to 0. We know dp divided by dt, rate of change of momentum is equal to force, isn't it? This is Newton's second law of motion. Force is equal to rate of change of linear momentum. If force is equal to 0, total force is equal to 0, what is momentum? Momentum remains a constant. Okay, so if total force acting on the rigid body equal to 0, momentum remains a constant. So this condition for translatory equilibrium, translational equilibrium. If total force acting on the rigid body is 0, then the total linear moment of the body remains constant, and this gives the translatory equilibrium. Clear, children? If force is equal to 0, total force acting on the rigid body equal to 0, momentum remains a constant, or we can say that momentum does not change with time. Now the system is said to be translational equilibrium. Okay. Now, if total torque on the rigid body is 0, the total angular moment of the body does not change with the time. So, we know torque is given by tau equal to dl divided by dt. Tau is rate of change of angular momentum. If total torque is equal to 0, if torque tau equal to 0, what is L? L remains a constant. So, the total torque acting on the rigid body is 0, the total angular momentum of the body does not change with the time. Does not change with the time means it remains constant. This gives rotational equilibrium of the rigid body. So mechanical equilibrium means it can be translational equilibrium and rotational equilibrium. What is the condition for translational equilibrium? Net force is equal to 0, linear momentum remains constant. What is the condition for rotational equilibrium? Net torque equal to 0, then angular momentum remains a constant. So this explains the mechanical equilibrium of a rigid body. In the chapter laws of motion, we have studied for equilibrium of a particle, the vector sum of all the forces on it must be 0. For example, on this particle, what are the forces acting? F1 and F2 and F3. Three forces are acting. Here F1 is acting in this direction, F2 is acting in this direction, F3 is acting in the other direction. So what is the resultant force? So we can F1 and F2, what is the direction of the resultant? If you complete the parallelogram, this is the direction result. Okay, and this resultant and F3 are in the opposite direction. Clear, children? So F3 and the resultant of F1 and F2 are in the opposite direction, and hence what is the net force? Net force is equal to 0. Now we can see that this particle is in translational equilibrium because the object is at rest, because net force acting on the particle is 0, and hence the object, the particle is at rest. So since all the forces acting on the single particle, the forces are coherent. Okay, children. So this already we have studied in the chapter laws of motion. So we know that an object, a body, a rigid body is in mechanical equilibrium if both rotational equilibrium and translational equilibrium conditions are satisfied. If both translational equilibrium and rotational equilibrium are applicable for a system, then we can say that the rigid body is in mechanical equilibrium. Okay, but a body may be in partial equilibrium, that is, it may be in rotational equilibrium but not in translational, or it may be in translational equilibrium and not in rotational. So in some cases the object shows the condition for translational equilibrium but does not show the condition for rotational, or in some other cases the rigid body shows the condition for rotational equilibrium but not able to show the condition for translational equilibrium. Now we can discuss some examples. So this is a rigid rod. AB is a rigid rod, okay, light rigid rod, and equal forces are acting at both the ends perpendicular to the rod. So F here, at the end B, a force acting in the downward direction. At the point A, at the end B, another force is acting in the downward direction. Both the forces are in the downward direction and have the same magnitude. So consider a light rod AB at the two ends A and B, of which two parallel forces both equal in magnitude are applied perpendicular to the rod. Okay, so both the forces are perpendicular to the rod and the magnitude of both the forces are equal. Now what is the net force? Because both the forces are acting in the same direction. So is the net force 0? No. Okay, because both the forces are reacting in the same direction. So net force is F plus F. Okay, net force is not equal to 0. But is there any rotational motion? No, the object does not rotate. Okay, so here if you consider this pen, both the forces are acting in the downward direction. Here one force is acting in the downward direction, another force is acting in the downward direction. So does the object rotates? No. So the object does not rotate. So we can say that since force is not equal to 0 and torque equal to 0, because the object does not rotate. Here net force is not equal to 0 but torque equal to 0. See, net force not equal to 0 but torque equal to 0. Net force is not equal to 0 but torque equal to 0. And since torque equal to 0, we can say that the system is in rotational equilibrium. That is the condition for rotational equilibrium. No, torque is 0, that is the condition for rotational equilibrium. So in this case the system exhibits or it shows rotational equilibrium. But net force is not equal to 0 and hence the system is not in translational equilibrium. Okay, children. So here in this case force is not equal to 0 and torque equal to 0 and hence rotational equilibrium is there, but the system is not in translational equilibrium. Consider the second case. Consider the rod, and here two forces are acting at the two ends in the opposite direction. Okay, here force is acting in the upward direction, on the other end force is acting in the downward direction. In this case, one force is acting in the upward direction, another force is acting in the downward direction. So consider a road AB. Here equal and opposite forces are acting at both ends of the road. So what is the net force here? One is acting in the upward direction, another one is acting in the downward direction. So what is the net force? Net force is equal to 0. Since these equal and opposite forces are acting at both the ends of the road, it causes anti-clockwise rotation. For example, this is the road. Here one force is acting in the upward direction, another force is acting in the downward direction. So what happens to the road? The road rotates, because here a force is acting in the upward direction. Here a force is acting in the downward direction. So what happens? One force is upward, one force is downward. Therefore the rod begins to rotate. Okay, it moves in which direction? Rotates in the anti-clockwise direction. So that is explained here. Since these equal and opposite forces are acting at both ends of the road, it causes anti-clockwise rotation of the road. Hence, torque is not equal to 0, because since the road rotates, torque is not equal to 0. Okay. And hence, the body has translational equilibrium. Because force is equal to 0, no? Equal and opposite forces are acting, therefore net force is equal to 0. Therefore the system has translational equilibrium, and since torque is not equal to 0, therefore the body does not has rotational equilibrium. Okay children, so here in this case both the forces are acting in the opposite direction, and because of equal and opposite force the road begins to rotate, and hence there is translational equilibrium, and since torque is not equal to 0, the object does not has rotational equilibrium. So that is the condition for partial equilibrium. So in the case of partial equilibrium, the body can have translational equilibrium but no rotational equilibrium, or the body can have rotational equilibrium but no translational equilibrium. So that is the condition for partial equilibrium of a rigid body. Pair of equal and opposite forces with different lines of action is called a couple or torque. So here the example, here equal and opposite force, the two forces are equal and opposite and they are acting at different lines of action, because one force is acting at this end, another force is acting at the other end. Okay, so lines of action are different. So two equivalent or a pair of equal and opposite forces with different lines of action is called a couple or torque, and this produces, a couple or a torque produces rotating effect. A couple produces rotation without any translation. So in this case these two forces represents a couple and they produce rotational motion, but there is no translatory motion. Okay. Example for this couple is, when we open the lid of a bottle, by turning it our fingers are applying a couple to the lid. For example, like this. This is a bottle. In order to open the lid of the bottle, here we have to apply a force in this direction, and here the force is acting in the opposite direction. So in order to open the lid, one force is acting in this direction, another force is acting in the opposite direction, like this. Here this force is acting in this direction, another force is acting in the opposite direction. So because of the couple, the lid of the bottle moves. Here one force is acting in this direction and another force is acting in the opposite direction. Because of this equal and opposite force, the lid moves. Here force is acting in the, here this force is acting in this direction and another force is acting in the opposite direction. Because of the couple, the lid of the bottle opens. Okay children, this is the best example for couple.